All right. So we're going to talk about the first enzyme, really, that we'll mention here. And we'll talk about superoxide dismutase. And I guess the first thing we got to do is define what superoxide means. And so something we kind of glossed over, didn't really talk about all that much, but, when we're talking about these oxygen transport proteins, we kind of just took for granted that, we breathe in oxygen, it gets bound in, iron or copper, whatever way it does. It gets moved around the body, and then, it just gets released, right? But, and especially with hemerythrin and hemocyanin, we talked about this, that there is a transfer, and even hemoglobin, to some extent, there's a transfer of an electron to the O2 species. And we never really talked about, okay, what happens to that, right? So, we need to kind of realize that oxygen is a good oxidizer, and it loves to grab electrons and kind of push this stuff around. And if it happens to grab an electron and turn into superoxide, which is this right here, O2 1 minus, it's a radical. That is a radical system, right? And the problem with that, right? The problem with that, sorry, I had a phone call there I have to deal with. And so the problem with radicals is that they are even more reactive, especially to organic species. And we didn't really talk about this, but this has to deal with the spin of the electrons and symmetry of, spin symmetry there. So that's a little bit beyond what we wanted to talk about here. If this was a full semester course of inorganic, we'd go back and, but just real briefly, if you go take a look in some of the papers that I posted for you guys, they'll usually give a, something like a spin 1/2 or a spin 3/2 or 7/2 or 5/2. They'll quote the spin of a system, and that's going to be extremely important because that tells us how many unpaired electrons there are, and there's an issue of, symmetry of, certain spin systems can only interact with other spin systems. But I am grossly oversimplifying this, but that's okay too, okay? So anyway, these radicals are particularly bad, and we need a very, very quick way of dealing with this, and superoxide dismutase is one way that our bodies take care of these things, okay? So overall, right, in general, briefly, I guess if we want to think about it, what superoxide dismutase will do is, through 2 steps, it'll take superoxides and turn it into O2 and peroxide. Okay, so we're going to go through a catalytic cycle. It's going to kick off O2 at one point, and it's going to kick off a peroxide at the other point there. Okay, and again, I'm not here to talk about necessarily the protein structure. I'm just going to focus in on the metals and how the metals are behaving. Right? You guys talked about catalytic cycles and all that kind of stuff in your other biochem courses. I'm just kind of drawing that attention in and focusing in on the metals themselves, okay? Couple of other quick notes. There are numerous types of superoxides, superoxide dismutases. The most common one, and the one that we'll be dealing with, is copper-zinc superoxide dismutase, okay? And so this is a bimetallic system, but it's a different metal, okay? Now, one of the most important things, not only to recognize the metal, but to also look at the oxidation states. And so what we'll see is that copper cycles between its 1+ and its 2+ oxidation state. But zinc's not going to do anything. It's just going to hang out there as a 2+, okay? There are also manganese superoxide dismutase. There's iron superoxide dismutase. There's nickel superoxide dismutase. Copper and the copper and manganese are the two that are, I believe, most commonly found in humans. The copper I know for sure. The manganese one, it'd be interesting to kind of go back and take a look at that one. But that's again, if we had all the time in the world and given all the time and space, then maybe we could do that. But that's okay. So we've got a bimetallic system. The copper is going to be the active site, okay? The copper is going to be the active site. The zinc in this case is there for structural purposes, okay? Now, we haven't talked about this yet, but one of the purposes of some metal centers is there purely as for structural reasons. That means they're there to kind of hold shape. Now, if you stop and you think about this for just a minute, or why this, could make sense, or how, think about this, right? What are the common geometries that you've run into for organic systems, right? So by far the most common thing is a tetrahedral geometry, right? We've got a carbon, it's got 4 bonds to it, right? Tetrahedral geometry. It could do square planar, right? It could do linear in some cases. And the same thing with nitrogen and, oxygen also, right? So if we're looking from a pure organic perspective, we're kind of limited in a way for our geometries, right? Tetrahedral is, tetrahedral and trigonal planar. Those are kind of our limited geometries. But as we move to metal systems, right, we can start to bring in trigonal bipyramidal or square pyramidal or octahedral or square planar, right? Metals have access to different structural geometries than organic systems do. And so in some cases, we'll see metals used as a structural site where they're just having a unique geometry that are kind of holding things in place. And that's what zinc is going to do, right? So the zinc, right, is going to be bound, it's going to be bound to an aspartate, I believe in this case. An aspartate or a glutamate, okay? So to a carboxylic acid, okay? And it's also going to be bound to some histidines, okay? And if I want to be better about this. And then what's unique is that this is also bound to an imidazole. Now I'm going to draw out this imidazole here because this is going to be a unique spot for this imidazole here, okay? So we got this and this, okay, and then this is tethered to the rest of the chain up here, okay. So that's what we expect to normally see with an imidazole. That's fine, that's great. But what's interesting about this is that this imidazole in this case is actually bound to the copper, which is going to be our active site. So this is a rare case where the imidazole is bridging in between two of these metals. Okay, and it's a deprotonated 1- imidazole here, okay? But before we get to the copper, let's look back at the zinc, right? So the zinc in this case has bound to 4 ligands, okay? So it's in a tetrahedral-esque geometry. It's a little bit distorted here, okay? But it is there to hold in one, I guess in general, right? It's there for a couple different reasons, but it's there in one case to hold this imidazole in place, okay? So one thing that's going to happen is that this imidazole here that's bridging is going to pop on and off that copper, and the zinc is kind of there to help hold things in place, okay? And as with every caveat, I always tell you guys, right, there's, more than one reason for why things are, right? But in this case, that's what we're kind of going to look at, all right? So let's look at the copper, okay? The copper is bound to that imidazole there, and it's also going to have a couple other histidines around it. In a kind of a distorted trigonal bipyramidal. So we've got some histidines kind of coming here, okay? This one's probably coming out at us, that one's kind of back, right? And then if we look at this in its resting state, okay, we've got a water molecule on here also, okay? And remember, these are all histidines, right? Histidine, okay. Cool, so the active site of superoxide dismutase looks sort of like this. A structural zinc, and it's 2+ oxidation state, 2 histidines, an aspartame or a glutamate, bound with a bridging histidine, imidazole there, to a copper, and it's 1+, it starts out in its 2+ oxidation state, with a couple of histidines and a water molecule around. So if you want to pause here and think, what did I tell you guys about water molecules, right? And what did I tell you guys about saturated coordination spheres and all that kind of stuff, okay? So let's pause here then, and let's tab over to the active site, right, or the crystal structure here, okay? So there's, if you guys want to pause here, and I'll scroll up here, If you guys go to the RCSB website and type in 1E9Q, it should bring you to what I'm looking at here. If you guys want to pause and do that, okay. So here is our crystal structure. This is bovine copper zinc superoxide dismutase. I'm looking at the ribbon structure up here in orange. All right. So let me get rid of that. You guys can see there's two active sites down here. This is just the copper-copper version, I believe, which is going to work in much the same way. Okay. But here's the copper-zinc version up here, which is what we want to kind of take a peek at. All right. So if we zoom in, there's our zinc here in that purplish gray, right? We've got our two... I wish I could get this to center for you guys a little bit better here. I'm sure there's a way to do it, but to be honest, I'm not 100%. There's our glutamate there in red, or our aspartate, or whatever it might be. There's our histidines here, and then the bridging imidazole there in the middle, right? So hopefully you guys can see the bridging imidazole there, right, highlighted in pink. Histidine, and then our carboxylic acid group right down here. Tetrahedral, pseudo-tetrahedral geometry. Here, right, is our copper, right? Histidine, okay? And you can see, as I try and scroll this over here, you can see how this is a distorted tetrahedron, right? There's an open site, right, an open spot that's kind of sitting right up here. And if I bring in my waters, right? So there's a lot of water in here, so I know it's kind of busy. But you guys see that guy right here, right? So that's our water that's sitting on our, or in the active site for our copper, above our copper there. Okay, so but let's just get rid of that, otherwise it gets a little bit cluttered. Cool. Let me bring back our, where is it? This should be, okay, there's our ribbons, right? Let's zoom out a bit and take a look at where the active site is. Now, you can almost see this if you know what you're looking for, and I'll make it a little bit easier in just a minute. You can almost see what it is, right? So if you take a look, remember here, right? This is our copper. There is where the magic's going to happen, right? And the zinc is only structural. So you can see how the structure of this is kind of blocking the zinc, but there's an open kind of channel for the substrate to come into or out of the copper center there, right? As you kind of rotate this around, you see how there's empty space there above that copper, okay? And to kind of drive this point home, let's switch to a space-filling model, okay? And right there, right? It's kind of tough to see, right? But you guys see the copper? It's not covered by anything, right? There's an open channel to get into and out of this, whereas the zinc, we can't see it at all. It's kind of buried underneath all this stuff that's over here, right? So the zinc is kind of buried over here, right? But the copper is kind of open, right? So the water can come in, the superoxide can come in, the stuff can leave and go out of this, right? But there is a channel that leads to this active site here, right? So I just wanted to draw this attention again to show you guys that, you know, look, right? There is... we should always take a look at where the active sites are in our enzymes. Okay. Cool. So if you guys want to, you know, sit here and take a look at this and peek around with things, then you know that's something good for you there, right? Let us go back to here. Okay. So let's sketch out just a simple, maybe, but just a simple catalytic cycle with what's going on. I'm just going to borrow this. So here's how things start. I'll just move this around. Here's how things start. Okay. The first thing that happens is, right, superoxide comes in, and the water is going to leave. Okay. And remember, this is going to come in and bind at the copper center here, right? So duplicate, move this here. I used to have to do this all by, you know, redraw everything, right? I'm glad I don't have to deal with all that. Okay. So this comes in, it does bind at an angle again, right? And there's a good resource here. I'll probably, I think I posted it for you guys already. But there is an arginine that's involved with this that kind of stabilizes and helps, kind of lock the superoxide and the peroxide in place over there. So there is some hydrogen bonding that's involved with this also. Okay. But, so similar to what we've talked about before with just how oxygen binds, all that kind of stuff, we see the same thing happening here, okay? We get some electrons that are transported in and out of this. We get some electrons that are shuffled around. Some protons come in, right? So we get in some H+. And what happens in this first step is oxygen gets kicked out. Now, we could spend hours just talking about how that comes in, the bonds that are getting formed, and all these kind of things. And it's cool, and it's interesting, and it's useful. But again, not really the point of what we want to do at the moment, okay? At the end of the day, what happens after this first step, right? So the superoxide gets turned into O2. And what happens is, now, along the way, the imidazole bridge, right, breaks. So it breaks off of the copper center itself. So we do have the zinc here still. It's still bound to its three groups, but we have, what happens is the imidazole bridge breaks and it becomes protonated, okay? And this is going to be important, all right? Because the next thing that happens, right, is more superoxide comes in. Right, so superoxide comes in, and it binds here to that copper center, okay? And let me try and draw this the best I can, okay? The imidazole, right, the imidazole hydrogen there is interacting and helping to stabilize, and it will, transport, or it will shuffle off an electron here in a moment, right? It will, let me just finish drawing because apparently I can't talk and draw at the same time. It will start to help stabilize that superoxide in this case, okay? And there is another hydrogen interaction with the rest of the chain that's over here, right? So we bring in another H+ that starts to interact with the arginine that's around. But that imidazole is helping to stabilize the second equivalent of superoxide that comes in. Okay? And just to finish things up, we kick off hydrogen peroxide in this case, H2O2. Okay? And then we end up back where we started. Right? This hydrogen gets kicked off with the peroxide, which reforms our bridge, and then more superoxide can come in. Okay? But this is a very simplistic view at the active site of superoxide dismutase. All right. Oh, I forgot to tell you one other important thing here. Well, yeah, that's fine. This is 1+, and then it goes back to the 2+, right? So there is a transfer from the copper to the superoxide in this step here, okay? To go back to the 2+. Right? Remember here it's 1+, 2+, 2+, 1, right? So electrons are kind of getting shuffled around here. The zinc doesn't change, right? It's always going to be 2+, right? And it's just sitting there to hold that imidazolate in place to kind of help with the hydrogen bonding and the stabilization. And it's cool, but I just, kind of wanted to talk to you guys about this at the beginning. And the imidazole there also kind of helps stabilize with some oxygen that's coming in and this kind of stuff. And there are more complex mechanisms that we could talk about and go through and all these kind of things, right? And if we had more time and if we were in person, we'd talk about the different things. The point being, two things I wanted to introduce with this, right? The idea of structural metals, okay? The idea of a structural metal, and I just wanted to kind of get you guys used to looking at a catalytic cycle, right? Paying attention to the oxidation states, the geometries that change, right, the ligands that are around there, what comes on, what comes off, taking a look at where the active site is for superoxide in the by looking at that space filling model there and kind of taking a peek at that. All right. So read through the article that I posted for you guys on there too, because it talks a little bit more in detail about these kind of things here. Okay? And I will see you guys on the next video then.